Good afternoon. In the previous class, we had a discussion on different types of addressing modes. Now, today, we would like to discuss about the assembly language programming. So, how do we write an assembly language programming? So, the topic for today's discussion is assembly language programming. The lecture objectives are this today's session will develop the students' knowledge on assembly language mnemonics and as well as assembly language directives, and how do we write the assembly language program. That is what the today's lecture objectives. And coming to this, the introduction part to assembly language programming. So generally, whatever the program we have written in any programming language, generally it is called it as a source program. Okay, so for example, in C language, if you write a program, then it is called it as a C source program. And in Java, if you write a program, then it is called it as a Java source program. Similar to that, if you write a program in assembly language, then it is called it as a assembly language source program. So this assembly language source program has to be converted into a machine language. That is what we are calling it as an object program. So this object program or a machine code is executed by your processor, and then we are going to get the output. So the program which is written using assembly language is called it as a source program, and if you translate that source program into machine language, so we require a translator. That is what we are calling it as assembler. So assembler is a system software which does the translation from assembly language program into the machine language program. So example, the most popular assembler is MASM. MASM is an assembler which is used for translating this assembly language program into machine language. So different types of instructions are available in the assembly language, because these we are saying it as a programming language, assembly language. We are saying that, so a language is always provides some set of instructions, different types of instructions it will provide. So using those different types of instructions, we can write a program using that particular language syntax and semantics. Syntax and semantics. So few types of instructions what this assembly language provides for us is example data transfer instructions and data uh, store load instructions, branching instructions, like that different types of instructions are available in the assembly language that we will discuss in this today's session. And another important point is that assembly language may be case sensitive, but it is not 100% case sensitive. Sometimes we may use uppercase letters when we are writing or when we are defining some assembler directives. So assembly language may be case sensitive, right? So when we want to write any program in the assembly language, so we are making use of certain mnemonic codes. We are using that assembly language mnemonic codes. So these are the few mnemonic codes which we will use corresponding to this opcode or a machine instruction. For example, if you take a load machine instruction, load and store, then the mnemonic we will use is LD for load, and store st for store, and move mov for move, exchange xch is exchange, in for input, out for output, push and pop. These are the different types of mnemonics that we can use to perform these type of operations: load, store, move, exchange, input, output, push and pop operations, etc. Fine. So then, for example, if you consider this instruction assembly language statement, so this is an assembly language instruction. If you say that, okay, so in this particular assembly language instruction, if you take, so in this assembly language instruction, here we are used a mnemonic. ST is the mnemonic we are used that. So this specifies what type of operation we have to do that. This is just is nothing but an alternative for opcode. Then these are the operands we are specifying that. So R2 and sum. This is a memory word. This is a processor register. So store R2 comma sum. Okay, so what we are doing here is that we are storing the R2 value into the memory word sum. So this is what it is doing that. So st represent the mnemonic, so corresponding to that store, so there will be a operation code which is represented equivalently in the binary pattern. So what type of operation we have to do that, so which is called it as an opcode. So that opcode is generally represented in the form of a binary pattern. So the assembler will translate this mnemonic or opcode value will be translated into a binary equivalent code, and that is used based on the operation the assembler can able to perform here. So the opcode value is followed by at least one or more blank spaces will be there. Okay, so a blank space or a tab character will be provided here, and later we have specified this as a operands. So the information that specifies the operands is given here. So the source operand is the and what is the destination operand. So store instruction is the store instruction. Okay, so what it does, that information will be provided here. So the operands are separated with the comma generally. Okay, and the destination operand is in the memory location. We are using sum is the destination operand, and source operand is R2 is the source operand. Processor register R2 is used here as a source operand. So this is a source operand, and this is a source operand R2, and this is the memory word sum is a destination operand, and this is the opcode. Fine. So this is what one instruction is. Then coming to this another example here in this instruction add add R2 comma R3 comma hash. So this is what, can anyone tell me what is this hash file? So this is nothing but immediate operand. Okay, immediate operand. So that is operand value is specified within the instruction itself. That is what file. And R2, R3 are the processor registers. So you cannot specify like this in this assembly language program. So you have to specify this instruction like this. So hash is not needed here in the assembly language program for specifying the immediate operand. You can directly specify like this. But when we are specifying this, when you are removing this hash symbol, so now add opcode becomes it as add So that indicates that I indicates that it is a immediate operand is specified in the instruction. Add I indicates that it is an immediate operand value is specified within the instruction itself. That difference you have to identify. Then next coming to this another example is load. LD stands for this is the mnemonic which is used for specifying the load operation, and these are the operands. Fine. So we are enclosing this R2, that is nothing but contents of R2, this which we are enclosing here. This is what the indexed type of addressing we are using here. Then coming to this, what are the different types of instructions that are provided in the assembly language? So the first type of instructions that are provided along with the mnemonics is the data transfer instructions. So generally the data transfer instructions are nothing but mainly two types of data transfer instructions are there. One is load, which is indicated with the mnemonic LD, okay, and another one is store, which is indicated with the ST, mnemonic code ST. So this load and store are actually the data transfer instructions. So based on how you are specifying the address of the operands, based on the address of the operand, you can specify and you can characterize what type of data transfer instruction it is. Okay, so for example, if you specify here ADR, LD space ADR, at least one space will be there here between this opcode and the operands. Okay, ADR here it is nothing but we are specifying the address directly, we are specifying here. So the register transfer is nothing but the load this the memory address specified with ADR. So this is the equivalent register transfer instruction, and this is the assembly language instruction. So RT, register transfer notation, we have seen earlier in the previous classroom discussion topic. RTN, we have seen that. Register transfer notation, we have seen that. So this is what RTN is basically. So this is a direct address, and then indirect address LD comma at the rate. If you prefix this address value, then it is called it as indirect address. So that is equivalently we will write this in the register transfer notation. And then there is the relative addressing here. When we are using relative addressing, we have to use the dollar symbol, and there is a immediate operand. We have to use this hash symbol. So then we can use this immediate operand notation. Then index addressing is nothing but ADR of X. That is nothing but we are using index addressing mechanism. So R1, this is a register addressing. Then if you are enclosing R1 in braces, then it is called it as register indirect addressing. And then R1 plus or minus, if you are specifying, that is auto increment addressing. Auto increment and auto decrement addressing, we can specify that. So this is what the different types of addressing of the operands along with this data transfer instruction load we have specified. And this is equivalent register transfer notation. Fine. This is what data transfer instruction is. Then coming to this data manipulation instructions. So the data manipulation instructions deals with the manipulation or updation of the data. So you can change the contents of the data, you can change here through this particular instructions. So you can increment the value stored in a memory address, or you can decrement the value stored in a memory address. So these are what we are calling it as arithmetic instructions: increment, decrement. And then this is a mnemonic. We have to understand what mnemonic we are using. So generally these you have to remember when we are writing an assembly language program. These are the mnemonics corresponding to these particular arithmetic operations: add, add, sub sub for subtraction, mul multiplication, div for division, adc this is add with carry, sub b this is subtract with borrow. These are the mnemonics which are provided in assembly language programming for performing these arithmetic operations. Similarly, this another category of data manipulation instructions which are called it as logical and bit manipulation instructions. So the logical instructions are nothing but this is and or, which we are calling it as. The mnemonics are and or we are using, and the CLR, which is used for clearing a particular memory word or a register, and then COM, which is used for complementing that value stored in that register or a memory word, complement operation. Then exclusive or XR, and then clear carry CLR C, and set carry SET set C. So CLRC set C, these are the clear carry and set carry. And then complement carry COM C. Okay, and then these are related to the interrupt. Okay, enable interrupt and disable interrupt, EI and DI. So these are logical and bit manipulation instructions. Then next coming to this shift instructions. So these are nothing but the logical shift right SHR, and this is a logical shift left SHL, and then this is arithmetic shift right SHRA, and then arithmetic shift left. Okay, this is SHLA. So A stands for arithmetic shift left, arithmetic shift right. Okay, and then this is rotate right and rotate left, and then rotate right with carry, rotate left with carry. So normal logical shift operations and arithmetic shift operations and rotation operations, and then rotation with carry, without carry. Okay, so these are operate on the binary data basically. Bit pattern it will operate that, so they are called it as the shift operators. Fine, all these three categories comes under data manipulation instructions. Then another important category of assembly language instructions is program control instructions. So which will control the program execution flow basically. So you can normally the program execution will be in sequence. Okay, that is in sequential order the program will be executed, like first instruction, next second instruction, next third, next fourth, like that. So which is controlled by your program counter register. Okay, and then instruction register, both are very important registers which are used when we are executing the machine instructions. So this we are already discussed in the classroom discussion topic on instructions and instruction sequencing. So now in order to alter this normal sequential flow of execution of the instructions, we can make use of this branching instructions which will control the flow of execution here. So BR is a branch instruction, JMP is a jump instruction, SKP is a skip instruction, and this call and return, these are used when we are making use of subroutines. Just like a functions, when we are writing in a program, we can make use of this call and return, we can use that. And this is CMP is a compare and TST is a test instruction. So these are what we are calling it as a program control instructions that we can use. Then another conditional branching instructions. This is based on some condition you want to branch the flow control at different locations. We can make use of these particular instructions. We can use that. So this is what branch if 0 bz. So that is if z value is 1, then this will be executed. If z value is 1, if z value is 1, so that is executed. B and z branch if not 0, that is z is equal to 0. That is a test condition. It will test whether z value is 0. If z value is not 0, then it will be branching will takes place. Branch if not 0. Okay. If z value is equal to 1, branch if 0, like that. So branch if carry. If carry is set with 1, so carry is flag. Okay. So this is a 0 flag. Z indicates that 0 flag bit, and this C indicates that carry flag bit, and S indicates that sign flag bit here, and V indicates that overflow flag bit. These are there in the register. Flag register will be there, so where we are storing this flag bit information. Basically based on this particular flag bits, the respective branching we can able to make here. So BZ branch if 0, B and Z branch if not 0. So that is a 0 flag is set or not. Based on that you can execute that. Branch if carry, branch if no carry, B and C. Okay. Branch if plus, branch if minus, BP and BM, that is if sign bit is set or not. S is equal to 0 or S is equal to 1. Branch if plus, branch if minus. Branch if overflow BV or BNV. Branch if no overflow. So these are what based on this particular Z, C, S and V. Overflow bit and sign bit and carry flag bit and sign 0 bit. Based on that you can able to perform the jump operation. So that is what conditional branching instructions which are provided in the assembly language. Now the reflection point 1 is here. This is one question for you, so anyone can able to answer. So identify which type of assembly language instructions are. So now tell me, this is the first instruction given for you, ADDI. So R2, R3, 5. So what type of assembly language instruction it is? Okay, whether it is a data transfer instruction, whether it is a data manipulation instruction, whether it is a logical instruction, or whether it is a branching instruction, like that you have to identify which type of instruction it is. Okay, then moving on to the next question. So LD, this is what another instruction, LD R3 comma R2. So what type of instructions these are? Okay, so anyone? So now the time for displaying of these answers for this. So ADDI is a data manipulation instruction. It will be used for manipulating of the data which is stored in any of these operands, either register operands or a memory word operands. You can do that. This is what data manipulation instruction, ADDI. Why I we have used here? Because immediate operand value is specified here. So that is the reason we have used I here. Then next LD, LD is nothing but it is a data transfer instruction. It is a data transfer instruction. Fine. So load, this is LD is load, ST for store. Fine. So now what are the assembler directives which are provided for us? Generally, this assembly language is also providing certain commands which are used by the assembler when it is translating the assembly language source program into an object program. So this assembler directives are nothing but the first important directive is origin. Origin is a directive which tells the assembler program where in the memory the data block will be stored. Okay, in the memory at what address the data block is started, that will be specified with origin directive. So this will tell to the assembler program. So assembler will look for the data in that particular address. Okay, origin specifies the starting address in the memory where the data block will start. The next directive is data word. This data word directive will specify that where that actual data word will be defined. So this is a directive used to inform the assembler that this is a data word. Okay. So for example, you are specified like this n colon data word 150. That means that n is a data word. So this n is a data word whose value is 150. Okay, so that is what the data word directive specifies that. So the data which is stored in this n memory identifier or memory location uh, named with n is storing the value 150. Okay, that is what the data word directive is used. Then the third important directive is reserve. So reserve directive is used to reserve the memory block to a particular memory word or to a particular variable. You can reserve a block of memory, you can reserve that. So this reserve directive is used for reserving a memory block for a particular data. Okay, so just like we will see, for example, if I want to reserve 4 bytes for a memory word sum. Okay, so we can make use of a reserve directive. So reserve some space 4, then you can write like this reserve. Okay, reserve sum 4, then it will reserve 4 bytes of data, 4 bytes of memory for this particular sum memory word. Fine. So that is reserve. And the last one is end is an assembler directive which is used as the last statement in the source program, assembler source program. It indicates that your assembly program has ended. Okay, so these are the few important assembler directives which are used in writing any assembly language program. Okay, and another important directive is EQU, so which is used for defining as some symbolic constants in the assembly programming. We can make use of EQ directive. So to specify some value, to store some value in a particular memory word name. For example, if I want to store a memory word 20 is a memory word whose value is equated to EQU is a directive which is used for equating 20 value to this memory word 20. So like that, here we can use EQU is another assembler directive, we can use that. Fine. So what are the assembler directives we have discussed now? So we discussed origin, data word, reserve, end, and EQ. So these are the few important assembler directives which are used when we are writing an assembly language program. So for example, consider this is an assembly language program which is given in the right side of this slide. We have given this assembly language program. So which is used for adding of n number of integers. So where n is storing how many number of integers you want to store. For example, if you see here the assembly directives what we are used in this program. So origin 200. That means origin 200 means that, so where your data is starting, so that is 200 is the memory word or memory address where your data blocks are going to be stored. So this is a data block. Sum is the data block we are storing here. So reserve 4. So sum reserve 4. That means we are reserving 4 bytes. 4 bytes of memory we are reserving for this sum. And origin specifies that your data is started from this memory address 200. Fine. Then next n data word. So n is a data word. Now it is having the value 150. Now you see here n is stored in 204. So because this sum is 4 bytes in length, and then 204 here 204 we have storing 150 n value. So n value is 150. That means you want to add 150 numbers, you want to add using this particular program. Then num1 is now at 208 because every word length is 4 bytes we have taken. So 100 8 12 16 like this it will be there. Every word length is 4 bytes. Fine. So now num1 reserve 600. So num1 reserve 600. So it is going to reserve 600 memory locations, it is going to reserve for that. 600 byte of memory locations it is going to reserve for num1. Okay, then it is the end is another directive we are using. So these are assembler directives which we are using basically. Fine. So now origin 100. So origin 100 specifies that your this is a assembler directive. Okay, origin is an assembler directive. Origin 100 here, this is what addressing our data information. So your program assembly language program is starting at 100 memory location. So what is that first instruction we have here? Load r2 comma n. So that means the n value we are loading into the processor register r2. So what is the value of n? So already we have stored the value of n is nothing but 150. So r2 is loaded with 150. This is the first instruction. This is the assembly language program instructions. These are what we are calling it as assembly language program instructions, which are available from 100 to memory address starting from 100 to 132. All these are the your assembly language program instructions, which are used for storing, which are used for calculating the summation of 150 numbers. Fine. So this is what the load. So the short form for or mnemonic for this is ld. ld r2 comma n. Then clear r3. That means what you want to do, you want to store 0 into this r3 register. So we are using clr r3. So clear mnemonic. Then move hash of num1 into r4. That means what we are moving here, the immediate the value immediate operand. This is num1, num1 value whatever we have, that we are moving into r4. So that we are specifying it as move r4 comma hash of num1. Then ld load r5 comma contents of r4. So r4 value we are moving that. That means first number we are loading into r4. That r4 value we are loading into r5. Then after that we are adding r3, r3, r5. So this is what the add instruction. So this instruction is going to perform this addition like this. R3 is nothing but R3 plus R5. The contents of R3 and contents of R5 will be added, and again it will be stored into R3. So this is the destination operand, and these are the source operands. R3, R5, this will act as a source operands, and R3 will act it as a destination operand in this particular instruction. Similarly, we are adding 4. We are adding 4 for R4, so that we are moving to the next number, because 208 is the address of num1, 212 is the address of num2. Like that we have 804 up to num(n). Totally 150 numbers are there, like this num150 up to that. Every number will be available in, every number will be available in 4 bytes away. Okay, so that's the reason R4 register value we are incrementing with uh, R4 register value we are incrementing with 4. Then R2 we are decrementing by 1, because one number is added. So R2 is loaded with an n value, which is nothing but 150. Now once one number is added, so it will be decremented by 1. So BGT, okay, branch if greater than. BGT is nothing but branch if greater than, if R2 and R0. So R2 and R0 value is compared here. So R2 and R0 value is compared, and if it is greater than, then it will branch to a loop instruction. So it will come to this statement, which is labeled with loop. So we have labeled this LD instruction with loop. So it will come to this here. Then again here, finally when this value becomes 0, R2 value becomes 0, then we will come out of this branching. Then after that, whatever the register which we are having R3 contains, that R3 contains is storing the result of summation of all the 150 integers. So that R3 value we are loading into the memory address named with sum. So this is what the program, assembly language program, which is used to perform the summation of n numbers, n integer values. So this is what the assembly language program, in which we have used different types of instructions. Branching instruction we have used, and then the data transfer instructions we have used, and data manipulation instructions like add and subtract we have used. Okay, and then here the clear instruction which we have used. Okay, all the different types of instructions we have used here in this particular program. Fine. So how these programs are going to be executed? This assembly language program, generally we are calling it as a source program written in the assembly language, and it will be translated or converted into a machine language by making use of a assembler. Once after translation, then only it will start the execution of that particular program by the processor. Fine. So this is what the execution of the assembly language programs. Okay, so now we are coming to this what we are calling it as this is what uh, we are calling it as just 1 minute. So how this assembly language program are executed and how the different operands are specified. Generally, when you specify the operand as an immediate value, that operand can be specified just by making use of this 8-bit binary notation. You can specify, or you can specify in the hexadecimal notation also. We can specify that. That is what the number notation. So in the operand itself, we can specify that. Fine. So now coming to this today's lecture level practice problem is that, so develop the code in assembly language to find the sum of 1 to n numbers. So it is very similar to this what we have discussed just now. So you are supposed to develop the assembly language code for performing this summation of 1 to n numbers. For example, if you are given n is equal to 50, you have to calculate the summation of 1 plus 2 plus 3 plus 4 plus 5 and so on plus 50. So summation of 1 to n natural number summation, you have to do that. Fine. So in this what we have discussed is we have calculated summation of n numbers. It may be not in sequence. There are n different numbers, integer number summation we have discussed. Small variation to that particular problem. Fine. Now coming to this today's lecture outcomes is that, so after listening to this today's classroom discussion topic, so you must be able to develop the assembly language code for solving any given task. So that is what the lecture outcome for this today's session. Fine. So any doubts you have, please let me uh, understand, or let me discuss the doubts. Fine. So if you don't have any doubts, so thank you one and all for patiently listening.